Cool. Okay, cool. Let me just maximize this. If during the presentation, there are something cut out, just let me know so I can reduce the resolution. Maybe this is better. Let me know. I will adjust the res. Okay. So just so thank you so much again for joining us. Let me just go through the agenda. So I'll just make a quick comments about the pre-lecture stuff because I added something else. And then I will go through the recap of last session. And then the new stuff will be this, they will go through the concept of vector space isomorphisms, product of linear operators, invertible linear operators, abstract general linear group. I'm calling it abstract because we want to define it on a abstract vector space. But in reality, for our purposes, we will be working more in the matrix linear group. The same with here, abstract eigenvectors and eigenvalues. This is just essentially will be defined on any vector space, in this case, finite dimensional vector space for our purposes in this module. The reason I'm doing that, like this general definition, is that most of you might have heard about eigenvectors and eigenvalues and associate these concepts with the matrices, but in generality, these things might not have anything to do with the matrices, and this is the case when you go to you do functional analysis, where you come across very strange looking operators with different have nothing to do with the matrices. Okay, that's one of the reasons why we are going through the giving you the concept, so you know that they might not have to do anything with matrices. Okay, even though we are working in finite dimensional spaces, which means in the end we will is in. Okay, and then I'll go through the study materials. Okay, so let's go through the module. So the only changes I did was to add an extra session here. So for those of you joining us for the first time, we are here, and hopefully today this will be green, and then next week we will move on to this section here, and some of the stuff that I could have covered here. I think it would have made the session too long, maybe 1 hour and a half or 1 hour and 40 minutes. So instead, I added some extra stuff, an extra session here, so we can take our time to go through this stuff before we get here. Okay. Okay, just in terms of the recap, first of all, let me just check the chat quickly. Does anyone have any questions about the additions to the class, to the next session? No? Okay, cool. Thank you. Okay, so I'll start here in terms of recapping. Last week we saw, for example, when V equals C2, the matrix ring, the elements of the matrix ring M2 of C indeed defines an operator, right? So we saw that you can for any element of M2 of C, you can define a linear operator like this, just like the normal matrix product of the 2x2 matrices with the column matrix. Okay. So we also mentioned that each matrix defines a linear operator, of course, as we've seen here. But this can also be generalized to Cn, where n is greater or equals to 2, for instance, or as a matter, which is what we are interested in. But it can be defined for any end. Okay. And another thing we asked was whether for any since any element of Mn of C can be associated with an operator, what about the other way around? Given an abstract operator, can we build a matrix representation of that? And the answer is yes, and we will do that in the next session. So yeah, in terms of building canonical operators, this is the I hope you've gone through the materials. The materials have more stuff, all these concrete stuff about operators, especially in Fn, where F is can be the field C. And then we look at, actually, let me just go back to see if anyone have any issues with the thing with the correspondence. Does anyone have any doubts about the n by n matrices are indeed naturally operators on Cn? Nobody has any doubts about that, right? Okay, cool. So another thing we saw was that if T is a linear operator, the range of T is defined like this. And then we saw that the range of T, I hope you were able to prove this, or at least saw the proof on the study materials, that the range of T is indeed a subspace of W, okay? And the dimension of the range is called the rank of T. And we also discussed that this concept of rank is coincides with when you talk about, when you take T to be a matrix operator, then it coincides with the notion of rank that some of you might have heard of in a kind of elementary linear algebra. Okay. Another thing we saw, another definition we went through, another concept, very important one, is that of kernel. We saw that the kernel of T from V to W is a set of all vectors that go to, are mapped into the zero of this other vector space. That's why I labeled it 0V, sorry, 0W. Okay, and we also saw that the kernel, another name, you probably seen that, because in the study materials, the kernel, the author does not use the term kernel, he uses null space. So that's another name for the kernel of T, okay? And another thing was that the kernel of T is also a subspace, not also, is a subspace of V, whereas the range is a subspace of W. So this is very interesting. And then this brings us to this other theorem. I hope I would like to think you managed to find a proof of this, that the dimension of V can be decomposed as the dimension of the kernel of T plus the dimension of the range of T. This is a very fundamental result in linear algebra called the dimension theorem, or some people call it the rank nullity theorem. So I hope you managed to get a proof of this. By the way, if you come across in some of the exercises that I ask you, or on the book they ask you to do like proof and these things, if you come across, like, if you reach the same result using different argumentation and these things, and your argumentation is different, you then find out when you are comparing it with the textbook or with my stuff when I provide a proof, it does not mean necessarily you are wrong. Okay, it's just often you can prove things in a different way. Okay, some proofs are more elegant than the others, but do not feel discouraged if the proof that you come up with is different from the one you find on the textbook. Okay, so there is no question, so I'll proceed. So the first definition of this session, let's dive straight into the concept of isomorphism. So a linear operator from V to W. By the way, I'm assuming T is the domain. The domain of T is an entire V. So I'm assuming that, which is natural, especially when we are dealing with finite dimensional vector spaces. So, but in an infinite dimensional case, it will be the case most often. The map does not cannot be defined on the entire vector space V. Okay, in the case of say a Hilbert space, for example, in the infinite dimensional case, we will see the concept of domain is very important. So T, you would have to specify which subspace of V that you are defining this map. But for us, it doesn't matter. We can take the domain to be the entire space V. Okay, so that being said, we say T is a surjective. I believe in English literature we call it onto, if the range of T is the entire space W, okay? In other words, for any W, for any psi prime in W, for any element of W, you will always find an element psi in V such that psi prime is the result of T psi, okay? And it's called injective one-to-one if for all for any two elements psi one, psi two in V, the corresponding results. So when you apply the operators are equal only if the two vectors are equal. Okay, so T acting on psi one equals T acting on psi two only if these two vectors, the two psi's are equal. Okay, so and then we say it's bijective if it's both surjective and injective. Okay, so this brings to the concept of isomorphism. So we say V is isomorphic to W, and this is we write this if there is at least a linear operator, a bijective linear operator from T to W, okay? So you only need to find one linear operator or construct one that's bijective for V to be isomorphic to W. And now I challenge you with this, obviously because an isomorphism is injective application, I'm using another term, an injective operator. It follows that T is an isomorphism only if the kernel of T is 0, okay? So I've added here 0V because obviously the kernel is defined on V, okay? So I challenge you to go and try to prove this, that T is isomorphism only if the kernel is 0. Let me just check. Okay, are we clear on all this? On the definition of isomorphism before I move on? Does anyone have any questions? First of all, can you still hear me? Because I haven't heard of any. So Barry is asking, what are we assuming? So, well, we are assuming, so what I'm saying is that T, so we are assuming, this is just a helper essentially. I'm saying because obviously if it's T is an isomorphism, then it's injective. So because of the injectivity, then obviously the T of psi equals 0 only if it's the 0 vector. That's what I meant. Okay, George is saying the sound is rough. Let me just adjust this. So I don't know if I addressed this the question, Barry. This is just an extra info I'm adding you. So I just essentially want that you prove that this T is only isomorphism only if the kernel is 0. So if the kernel is not 0, then T is not an isomorphism. Okay. Are we clear on that? Okay. By the way, thank you so much for the guys on the chat. Soham, yeah, thank you. I didn't actually realize, obviously, because I was late. I didn't see. I couldn't bring Soham on the thing. So Amir. Yeah, so Amir, the reason I'm writing 0 V here is to distinguish. This is the 0 of V, right? Because this is the T, the operator is going from V to W to distinguish from the other 0. So you know, and the kernel is because the kernel is defined for elements of V. That's why I in fact, I'm being so nice because in many textbooks, they will just write 0 and then you don't know which 0. Obviously, it's obvious that even if I didn't label this 0V, it would be like the V of, sorry, the 0 of V, because the kernel is defined on this side for the elements of V. Does that answer? Okay. I'll come back to the thing at the end, just for the purpose of the thing for us to move. I will come back to the chat again. Okay, so let's see an example of an isomorphism. Okay, so imagine we have, in this case, we have C4, right, with these entries, A, B, C, D, where A, B, C, obviously, A, B, C, D are complex numbers. And then we have M2 of C, which we have seen is happens to be a ring, but I hope some of you also figure it out that M2 of C can also be seen as a vector space over C, right? In fact, this is a property that makes M2 of C very interesting because it's a ring, it's also a vector space. This makes it into something we call an algebra. In this case, this happens to be a very interesting algebra called the C-star algebra. We will, I think, in some in the future sessions, in the future in the advanced section, we might touch C-star algebras. But this is a prototype, a typical prototype of C-star algebra. So we in the intro of it in the ring section, we viewed it as a ring, but we can also view it as a vector space over C. So anyway. We can define a linear operator as this, So you take any element psi, and then you map it into this, right? And I leave it for you to see that this definition of T indeed makes T into an isomorphism from C4 to M2 of C. By the way, as a challenge, I challenge you to find what would be the canonical, the basis of M2 of C. Okay. So let me move on. I hope there is no question about this. Okay. You can take this to the chat. Now, here's a very important result is that if V and W are vector spaces over C, then the two are isomorphic only if they have the same dimension. Okay, so I claim you might be able to prove this. So I'll leave it as a home challenge. If you cannot, the result is also on the study materials, or if you don't like that, if the study material is still confusing, you can ping me on the GitHub. I can provide you my own reasoning on proof of a version of this. But you can prove this. Just reason from the things that you learn about, bases and dimensions and these things, and now isomorphism. You should be able to prove this. Maybe another way of doing this, saying this also would be these statements are equivalent by that we mean one implies the other. So if V and W are isomorphic, then immediately follow that the dimension of V and W are the same, and vice versa. Okay, so if you prove the two have the same dimension, then you can construct an isomorphism between the two by using the basis, the basis from the basis from one to the other. Okay, so you can use the basis to prove that if there are they have the same dimension, you can use the basis of the two spaces to prove that they are isomorphic by using the basis to construct a linear operator, an isomorphism between the two spaces. Okay, let me just check before I go. This is another important, very important result is this one. Let me just check this chat first. Okay. Apologies. I have a bit of symptoms of cold. Okay, so this other result, if V is a vector space over C and the dimension of V happens to be n, then V is isomorphic to Cn. This is very important result, which means if you build any abstract, if you build any abstract vector space, no matter how abstract it is, if the dimension of it is n, then it's isomorphic to Cn. So that means the reason why this is very interesting, it means sometimes you can build a very abstract spaces, but they are very hard to work with. In our case, because Cn, we can have it as like in matrix form, for instance, it's easier to work with. So in that case, instead of working with an abstract vector space, if you know that vector space is isomorphic to Cn, we can immediately start working with Cn instead, because it's much more easier to handle, right? So for example, here you can see that when V, by the way, for those of you who don't know what tensor product is, that's fine. I'm just mentioning this because I know some of you are a little bit advanced. We will come back to tensor product after in the Hilbert space section, but in here, because this the tensor product of C2 with itself has dimension 4, it means it's isomorphic to C4. So therefore, you can work with C4, elements of C4. So then it's just a matter of translating, the elements of this that you want to work with this. Obviously, for some of you already coming from quantum mechanics and quantum computing, there's a bit of something very interesting that happens, is that there are some vectors here that cannot be decomposed as tensor product of individual elements of these two spaces. But we'll come back. We'll come to that in the Hilbert space section. I don't want to go through that at the moment. Okay. So the key to note is that if you have any vector space of dimension n, no matter how abstract the construction, it will immediately be, it follows that this is, it's isomorphic to Cn. So you can just use Cn instead to do, you can do the theory on it, but maybe in practical computation stuff, you can just use Cn instead, okay? So this is very important result. You might see, I think the textbook has, the study material has a proof of this, and you can also find the proofs anywhere. If you cannot, then you can, maybe in the next session after I do the, after we go through how you transfer, how do you go from linear operator to matrices, when the matrix representation of a linear operator, then maybe then you will be able to prove this, okay? To prove it. So let me just, okay. So thank you so much, Soham, again for the help in the chat. In fact, I might pull you on the thing, or yeah, it's okay. I'll go through. Okay, so are we clear on this? Does anyone have any questions about isomorphisms? Okay, so if I give you two vector spaces, all you have to prove if they are isomorphic, then they must be at least a linear operator that's that satisfies the concept, the conditions of isomorphism that we define. Okay. And sometimes you don't even need to look, if you know that the dimension of that vector space is, finite, for example, in our case, that's what we are interested in, then you know immediately that it's isomorphic to Cn, okay? So you can just work with Cn instead. So this is really very important result, Okay, so now let's switch gear a little bit. So now instead of considering a vector space, sorry, a linear operator going from V to another vector space W, let's consider a linear operators going from V to V, okay? So we define the identity operator, I will call it IV, because it goes from V to itself, as this. So it's an operator that does nothing to the elements. So it takes an element to itself, okay? So this is, of course, a linear operator, and I guess it's obvious. And as you can see, this is another challenge, because it's one-to-one. What would be the kernel of this operator? What could be? What is the kernel of IV? 0V, exactly. Well done. I'm very happy, proud of you guys. It means that I haven't lost you. Huh? So yeah, indeed, the kernel is 0. Okay. So going back to concreteness, if we have like a V equals Cn, then obviously IV correspond to the identity matrix, right? And this can also be, of course, generalized to Cn, where IV becomes the identity matrix, of M2 of C. Okay. Next week we will work with this. We'll define this in more concrete. So far, we've been defining it as a proxy of M2 of C, but yeah. But next week you will take it's just essentially just n by n matrices, right? The set of n by n matrices, which also forms a ring, and it's also a vector space, right? So anyway, the identity of this can also be obviously is also the identity matrix of it. Okay. A convention that we will make is whenever V is understood from the context, instead of writing IV, repeating ourselves, we'll just write I. Okay. So if you see I, you don't see me write IV, or IC when we are talking with a concrete vector space. Just assume it's the identity. Okay, define as this. Let me check the chat. So I believe we are all on the same page. Does anyone have any questions so far about this? Okay, that's great. This is all good. So far, so good. Excellent. Okay, so let's define the product, what we understand as a product in the abstract sense. You will see that obviously in the matrix sense, the product of all matrix operators will be the product of matrices, but let's not go there for now. Let's worry about that in the next session. So when we have an operator T1 from V to V and another one from V to V, their composition, did we cover composition in the lecture about sets? It doesn't matter anyway. So the composition of the two operators defined like this, that also goes from V to V, is defined like this. So you apply T1 first to psi, and then the results of that, you apply T2. Okay? So it's like T1 psi, then the results, you apply the second operator. Okay? So you can, I leave it as an exercise for you to prove that the composition of two linear operators is also a linear operator, okay? And as a convention, instead of writing this like this circle, we'll just write T2 like this, like a product, without writing this, okay? And we'll call it a product operator instead of composition, because composition is more suitable for a plain set without structure on it. Now we are using the linear structure. Well, let's just call it, product. Okay. In sometime in the next few sessions, we might also, when we're talking about dual spaces, we will define the addition also of operators. Okay. But for now, we'll just let's just stick with the product. Okay. So that's how the product of two operators in V both of them acting in V are defined. Okay, is defined the product. And then this motivates another definition, a very fundamental one, that an operator is invertible if there exists another linear operator that we call denote T minus 1, that also obviously goes from V to V, such that the product between them gives the identity. Okay, so again, so this means that not every operator, because otherwise we wouldn't define it, right? This means that not every operator acting on V is invertible. Okay, otherwise we wouldn't talk about it. So that this then brings another question: is that what is the is there a necessary and a sufficient condition for an operator to be invertible? Is there something that they need to satisfy to be invertible? That, when it satisfies that, we know immediately that's invertible. Yes, bijectivity, yes, that's indeed well done. indeed, that's a condition to satisfy this. Or there's another way of saying it is a linear operator T is invertible if only if the kernel is 0. Okay. Notice here I'm writing 0 because obviously it's understood that the operator is going from V to V, right? There's no need for me to write 0V. Okay. So there you go. Okay. So that means, as one of you I think is Aditya saying, like has to be bijective. So it's if it's bijective, then obviously the kernel is 0, right? So it's the same thing. So T is invertible if only if it's bijective, because obviously being bijective also is like, you know, having the kernel 0. Okay. So that means obviously if T is invertible, then you know, T is also an isomorphism, right? So okay. Another important result is this is why invertibility and the thing is very important. When you have two invertible operators, their composition, their product is also invertible. Okay. So this is very interesting. So, you know, here's some toy examples that, you know, all of you guys coming from, you know, coming from quantum computing or quantum mechanics will be familiar that these guys are invertible, right? Okay. So now the question then is, now that we've seen that, you know, the product of two invertible operators is invertible, that means invertibility is closed under product. Now, what in structure that in early on that you know, you could take like a group structure, for instance, you know, does that mean, you know, do you think that then the set of all invertible operators forms a group? Who thinks that? Who thinks yes? That the product, the set of all invertible operators is a group? Yes, and it's true. It is true. So we'll see this. Again, well done. Indeed, this is what we call the general linear group on V. So it's the set of all operators from V to V such that you know, they are invertible. Okay, so I called it abstract because obviously, you know, to distinguish it, you know, that it's a well-defined concept for any vector space. It doesn't matter whether it's finite dimensional or infinite dimensional. Obviously, for us, the most interesting thing for us is when V is finite dimensional. Okay, and in that case, later, I think in the matrix group section, in few sessions time, we will see that if the dimension of V equals n, then this group is isomorphic to the matrix general linear group that we already, I think in the group section we hinted what it is, but we will come back to that again. So this is very interesting. This shows again how the concept of dimension is a very intrinsic concept on a vector space. Okay, so this means if we have a vector space that of dimension n, instead of working on the abstract operators in here, you know, the invertible operators here, we can just work with the matrices instead. Okay, so this is very fundamental result. We will see this once we get to the matrix group section. Okay. So this, you will see also, this is the matrix group section. We will deal with the unitary groups and a special something called a subgroup of itself called the special unitary group. These are very important groups in quantum mechanics. Okay, so UN is a subgroup of this, but this is a subgroup of this. We will see. I'm just giving you some sort of excitement as opposed to wanting to dive deep into them for now, anyway, because we haven't really defined what what unitary operator is. Okay, but I'm just giving you kind of a taste of what's coming. Okay, and unitary group is obviously very important in quantum mechanics, because mathematically, let's say it's the thing that's behind the so-called unitary evolution. The evolution that happens in a quantum system when there is no disturbance. When you are not making measurement or disturbing the system. Okay, this is something that the physicists on the audience can maybe elaborate more on. Okay, so now it brings me to the section of eigenvectors and eigenvalues. Again, the reason I'm defining it in this general terms, and it's just that, we won't do much about it, because in actual reality, in terms of working with, we will do that in the context of, after we've gone through the concept of Hilbert spaces, okay? That's where, because that's what matters to us. Of course, we can argue that Cn, is already a Hilbert space under the hood, but we are not dressing Cn yet with the Hilbert space costume yet. So yeah, so the reason I wanted anyway to define this is for you guys to see that the concept of eigenvectors and eigenvalues are general concepts. They might not have to do anything with matrices whatsoever, okay? Which is the case when you come into functional analysis. Nevertheless, when we deal with the finite dimensional spaces, then because as you have seen, operators and matrices are the same thing. So you can indeed define, use the matrix notion as being equivalent to the abstract, okay, in the finite dimensional case. So having said that, so we say a vector. So first of all, let's T be an operator from V to itself. And then we say a vector is an eigenvector of T if there exists a lambda in C, a non-zero element, obviously, such that T psi is the same as, multiplying lambda with multiplying psi with lambda, okay? So the lambda is then called the eigenvalue of T, okay? So to recap, the eigenvector is a vector, the eigenvalue is a scalar, okay? And the set of all eigenvalues of T is called the spectrum of T, and it's often denoted like this. So in other words, lambda is an eigenvalue of T if there exists a vector in V, that's an eigenvector of T with respect to lambda. So this is a very important concept to kind of to wrap your head around. Let me check the chat. Okay, does anyone have any? I mean, some of you already, already read, quantum computing textbooks and stuff. It's quantum mechanics and these things. Eigenvalues and eigenvectors are all about, are all over these introductory textbooks and these things. Maybe the way it was introduced to you, maybe it was through the matrix thing, not in this abstract form. Okay, and we will elaborate more on this as we go along, until we get to the actual, concrete matrix stuff, where we will, you will learn how to, the techniques to, giving an operator, how do you diagonalize it? How do you find the eigenvalues of the operator? We'll go through that I think it's in the last section of this module, which is to do with quantum operators. But it's a very important concept. And this actually, let's say in the context of a quantum mechanics, I'm just giving you a little bit of flavor, not wanting to go direct conversation today on that, because we haven't even defined Hilbert space yet. So in quantum mechanics, you are interested in eigenvalues that are real numbers, okay? In fact, you are interested in operators called Hermitian operators, in our case, because we are in finite dimensional vector spaces. If we were to talk more concrete, we will say self-adjoint operators. But anyway, you are interested in operators whose eigenvalues are real numbers. Of course, real numbers are also complex numbers. So what that in reality means the lambdas have to have only real parts. They won't have complex parts. So they will be real numbers, because obviously when you make a measurement, of an operator, encoding a physical observable, then the result is obviously, you have the result is a real number, right? That's what probes and whatever the experimental stuff you set up, they don't spit out complex numbers, right? They spit out real numbers. So this is a very interesting concept for you to wrap up around your head. Not just in terms of finite dimensional thing. We'll see in the infinite dimensional case, you have to tweak a bit this thing. But yeah, we'll come to that in the advanced module. Okay, and here's a very interesting theorem. If T is a linear operator with distinct eigenvalues, lambda 1, lambda 2 to lambda n, with their respective eigenvectors, then their eigenvectors are linearly independent. This is very interesting, isn't it? Can anyone see why this is interesting? Why make a fuss about? Why is this interesting? That this thing that when you have these eigenvalues, in this case that are distinct, then their corresponding eigenvectors are linearly independent. Basis, exactly. That's right. Basis. So that means these are candidates to be bases, right? Because bases are linearly independent. Okay. And in fact, so this is the question then for you to scratch your head, is that can the eigenvectors of these distinct eigenvalues form a basis for V if the dimension of V equals n? Okay, so we have, the sequence goes to n. So the claim is if the dimension of V happens to be n, if these bases form if these eigenvectors form a basis. So that's the question for you. Go and think about it. You don't have to answer now. It's very interesting, because then it means if you have an operator, say for example, okay, let me give a quantum hint again. Even though we are not there yet. Imagine if this was the Hamiltonian, for instance. This operator was encoded in the Hamiltonian, and imagine V is a Hilbert space. I know we haven't defined Hilbert space yet. This is very interesting, isn't it? And another thing. Can you guys see the button also? This thing. This is something that you should be aware of. Let me just actually go up. So in terms of notation, sometimes I found it very annoying. Sometimes physicists, they write this. So if you see this, they mean these are the eigenvalues, the eigenvectors corresponding to obviously the lambdas are eigenvalues, but the reason they put it inside the ket is that they want you to consider the ket as the corresponding eigenvectors. Okay? So this is the thing. This is one of the things that I find it a little bit, yes, indeed. Physicists do a lot of, thank you, Bahari. I'm glad we agree on this. Sorry to the physicists, to Soham and the other. I know Soham doesn't do this. he's a mathematically cool physicist. So yeah. So yeah, bear in mind in the notation, if you find this, often they don't say. Sometimes they won't even use lambda. They maybe use E, for instance, and place it there, and then you look, what's this? It's one of those things that you just have to kind of learn how to live with, especially if you are interested with physics stuff. I particularly find the Dirac notation very well. It's useful in some sense, but it's a little bit annoying. As we go along, you will see, especially when you deal with infinite dimensional spaces, it becomes a little bit the net benefit for me, it's it kind of the net benefit drops, but nevertheless, it's used. It's like the standard notation. So yeah. Okay. So are we all clear in terms of eigenvectors and eigenvalues? We will get we'll dive more into these. In general, a lot of the stuff that I'm not covering at the moment, I could have covered them. For example, tensor product, we could have done it now. I think it's better to do them in the context of a Hilbert space. Obviously, they can be defined on any vector space, but then we don't have to repeat ourselves again. Okay, we do it all in the kind of in a much more contextual stuff. Obviously, there are some things I'm doing the opposite, which is define them now, and then later we have less to care about. I mean, less to go through. So yeah. Okay, so we are all clear about eigenvectors and eigenvalues. And most importantly, the message is these concepts are very general concepts, okay? They might not have anything to do with the matrices, okay? I'm going to tell you a story, a funny story of an interview we do that in our company sometimes when we interview people. Sometimes we throw very strange operators, say, what's the thing? What can you say about the eigenvalues and eigenvectors of these operators? And sometimes some of the guys, because they associate the concept with the thing, they will kind of you see them a little bit confused to say, but what's the matrix representation of this? What's the matrix and these things? Okay, so the message is really that these concepts are very very general concepts. They might not do anything with the matrices whatsoever. They have to do in finite dimensional cases, which happens to be this module. But when you go to infinite dimensional case, it's not. You will come across operators that have nothing to do with matrices. Okay, so I know I've repeated this several times. Hopefully, it's kind of stuck. Okay, so as a home challenge, this is probably trivial for a lot of you, especially those guys who are already coming from quantum computing and these things. Try to you can use software, by the way. NumPy, SymPy, or Qiskit or whatever. Go and try to find the thing. For the ones who are not who haven't come across it, try to find. I know we haven't we haven't gone through the techniques yet on how, given an operator, how do you find their eigenvalues and eigenvectors. But for those of you who already come across, I challenge you. I mean, for those of you who already I know are coming from quantum mechanics and quantum computation, they have already seen these things. You can do this, with maybe a software or something. And then the question is, do the eigenvectors form a basis for C2? This might be a little bit harder. It takes a little bit for you to think, but maybe some of you will find it okay. That brings me to the study material. We'll stick with Professor Axler, linear algebra done right. So today we'll have two sections because obviously we are covering different main concept that they are important. Okay, so that they are not in the book. They are not like close to each other. They are not attached to each other. So the first section that you should worry about is the invertibility of linear maps. I believe that's pages 80 and 88. Go there and see, go through it again, the concept, and do some exercises. I believe the book has some exercises. Get yourself familiarized with invertible linear maps in the abstract sense. Okay, and then I believe it's section 5a, which deals with eigenvalues and eigenvectors, and that's pages 131 to 132. And you will have other stuff there in this section. If you want to go through those other extra stuff, that's fine. That I haven't covered today. That's fine. The reason I haven't covered a lot of stuff indeed is because they will be covered as we go along, as we need them. Okay, to make the I hope to make the learning a little bit more easier especially for those of you not coming from a physics or mathematics background. Okay, so that's it really. I don't believe, yeah, of course. I need to mention again, this session is available for replay always on YouTube. If you, want to replay again, and you can find the study materials on GitHub. I will upload them, and yeah, if you haven't joined the Gitter, I really encourage you to join the Gitter, because then you can ask not just questions where hopefully someone can help you. If somebody cannot help, nobody can help you, I can jump in and try help you. Okay, so that's the benefit of joining the Gitter channel. With that, question, Paris. C2. Yes, C2 is isomorphic. Yeah. The decomposition, this is something that we will talk about. We can pick it up later on the thing. The entanglement stuff has to do with the way the tensor product, obviously, when, even though the two spaces are isomorphic, but the way, the definition of, this is just a sloppy, way I'm doing it now, because I haven't defined the tensor product yet. But the way it's defined, it means that you cannot, even though the fact that the two vector spaces, are isomorphic, and in the case of C4, you are not able to decompose the thing, has nothing to do with the isomorphism. It's just the way, the nature. In fact, actually, as an exercise, I would challenge you to see whether the tensor product, the way you tensor two elements in the two spaces, and then to get the elements of the four spaces. Check if that's linear. Okay. And do not mistake the product of operators with the product of the vectors. Yes, exactly. Thank you, Soham, for clarifying this. Yeah. Anyway, this is something that we will come to. It will come. We will have a section on tensor products once we define the Hilbert spaces. As I said, we could have defined this, okay, now, but I think it's for the benefit to put everything into context. It's probably better to go through tensor product after the Hilbert space section, because then you can see the full consequences of some of the stuff like entanglement and these other stuff that are consequences of technical consequences. Okay. So. Okay, Aditya is typing, but because I didn't follow the question with George, I encourage you guys to take it up to the chat. Okay. Okay. Do we have any other question? Maybe I can bring our friend Soham to see if I missed any question because I haven't been checking the chat, and let's see. I'm going to bring you, Soham.
Hi. Yeah, I don't think you missed any. Probably all of them are answered actually.
Okay. Okay, good. Thank you, Amir. And yeah, I hope it's. I know, like it's been like a very like. We could have gone through a lot in one session, but I think this like slow, this approach of not overwhelming you with too many things, but instead in like small chunks, it's probably more helpful than going into a massive session with like 1 hour and a half or 2 hours. So yeah, so next week we'll go through this. We'll start first with some of the stuff that I didn't cover today. I want to cover here, and then we will do the transfer, the correspondence, giving a linear operator, how do we build a matrix representation of that? Okay, we will do that, and then we will immediately start working from now on with matrices. Okay, no more abstract operators, and we will also start immediately working with CN, no more abstract vector spaces. So it will always be CN. Obviously, then we will dress CN with the Hilbert space structure, and we might actually also mention Banach spaces. But yeah, let's see. So that's it for today, and I hope you kind of got something new about it, even if you already knew a lot of these concepts, maybe from a different angle. Hopefully that's useful to you. And yeah, and we catch up next week. Unless you have anything to comment, Soham, or anything that I missed, or yourself.
Nope. I think that's all.
Okay.
Thank you.
Cool. Barry, oops. Okay. Okay, in that case, thank you so much, everyone, for tuning in. And well, we see you next week. We are getting there, okay? The Hilbert space section. I know you are all excited about getting to the Hilbert spaces and maybe the quantum stuff, you know, at least on the mathematical side. Okay, so have a good weekend, everyone. And thank you, Soham, again, for your help. And yeah.
Thank you. See you all. Bye.